Hi everyone, this is Shiva Biram signing in. Welcome to the fourth session of electrical traction. In this session I am going to explain you tractive effort and the derivations related to that. Basically tractive effort is nothing but the force required or the force developed by the traction motors in order to develop the mechanical power. This is going to have three components of forces. One is the force required by the traction motors in order to develop the required acceleration, both linear and angular. And the second one is the force required to overcome the resistance of the train. Let us see what is meant by the resistance of the train. What are the different types of resistances we are going to have, like track resistance or wind resistance, whatever it may be. And the third component of force is to overcome the gravitational pull. This thing is to be considered when the vehicle moves upward gradient or downward gradient. So all these things we are going to consider in this session. So it is the force developed by the traction motors, and here we consider the Newton's second law of motion, that is the force required is equal to the product of mass and acceleration. Generally the mass of the train is going to be represented in terms of tons, and the acceleration alpha is going to be represented in terms of kmph/ps, kilometer per hour per second. And to get the newtons we need to have kg meter per second square. So the tons are to be converted into kilograms. So 1 ton is equal to 1000 kgs, and kmph/ps, kilometer per hours per second. So km kilometers means 1000, per hour means 3600 seconds. So this is to be multiplied with 1000 by 3600 in order to get the meters per second square for the acceleration. So here the force is equal to the product of mass and acceleration, and here W is the actual weight of the train converted into kilograms, because W will be in tons, and when it is multiplied with 1000 we get the kilograms. And generally alpha will be in kmph/ps, kilometer per hour per second, and in order to convert that into meters per second square we have to multiply with 1000 by 3600. Ultimately we get here kg meter per second square or newtons. And if we simplify this we get 277.8 W into alpha. And one important point to consider here is at the beginning or at the starting, when the vehicle moves, there will be some inertia with respect to the moving parts or rotating parts of the train. Hence we need to consider the effect of rotational inertia of the moving parts. Generally this rotational inertia of the moving parts will be expressed as a percentage of the weight of the train, that is considered as W dash. Hence at the beginning the total weight or the effective weight of the train will be the sum of the actual weight of the train W plus W dash, which is the effect of rotational inertia expressed as a percentage of this actual weight of the train. Hence if you consider WE as the effective weight, it will be equal to W plus W dash. This is one of the important things to be considered at the beginning only. And once the train comes into motion, moving, obviously this W dash will not be there, because already it is in moving position. So here the effective weight is considered as WE equal to W plus W dash. Just now we have seen that W is the actual weight of the train and W dash is the effect of rotational inertia. Now let us consider the gravitational pull. This gravitational pull will be there when the vehicle moves against gravity, that is when it moves through an upward gradient. So here we consider theta as the upward gradient making with the horizontal. This is the horizontal line we are considering, and this is the slope or the gradient that we consider on which the vehicle moves. So here theta is the gradient we are considering, and this is the train or the vehicle which is moving upwards, and generally the weight is going to act exactly downwards, and this is the component of force. So if this is a weight and this angle also will be equal to theta, this portion also is going to be equal to theta, and this component of weight will be W cos theta, which is compensated by the normal reaction of the vehicle, and this component of force. So when you divide this into two components, one will be W cos theta, another one will be equal to W sin theta, which is the gravitational pull on that object, and we need to compensate this component of force. This means the tractive effort should have this component of force also in order to overcome the gravitational pull. I hope it is clear to you. So W sin theta, and here generally W is we know that it is represented in tons, and we can have, in order to convert into kilograms, it is to be multiplied with 1000. And in the case of traction applications, sin theta is going to be represented as a percentage of gradient. So generally it is expressed as sin theta as G by 100. And when it is multiplied with 9.81, that is acceleration due to gravity, we get the force in terms of newtons. So here Fg is given as 1000 multiplied by W sin theta. So 1000 is here because of we are converting the tons into kilograms, and 9.81 is acceleration due to gravity, and G is expressed as sin theta by sin theta is expressed as a percentage of gradient, so G by 100. And when substitute all these things, we are going to have Fg is equal to 98.1 W into G newtons. And this component of force will be positive when the vehicle moves an upward gradient, and it will be negative when it moves a downward gradient. So it will have both signs, plus or minus, positive for upward gradient and negative for downward gradient. Now the tractive effort to overcome the resistance of the train, and the train resistance is due to mainly the track. Of course the rotational inertia will be very much less, but still there will be some resistance to the motion of the train, and also the wind resistance and the resistance of the moving parts. So all these things will come into the picture. So we need to develop the tractive effort to overcome the resistance of the train also, and generally it is expressed as R, the resistance in newtons per tons. This will be given for us, and if it is multiplied by the actual weight of the train, that will give us the component of force or the tractive effort required to overcome the resistance. So frictional forces internal to, these are the resistances that we are going to have: axial guides, bogie pivots, buffers, etc., and external to the rolling stock, friction between wheels and rails, flange friction, resistance as a resultant of temporary deflection of track, aerodynamic drag. So here Fr is given as the force required to overcome the resistance of the train is given as W multiplied by R, where W is the actual weight of the train and R is the resistance, which is represented in newtons per tons. So obviously newtons per tons multiplied by tons will give us the force component Newton. So ultimately the tractive effort required is going to have three components: Fa and Fg and Fr. So the total tractive effort now it becomes equal to F is equal to Fa plus Fr plus or minus Fg, where Fg is positive for upward gradient and minus for the downward gradient. So this is the final expression we are going to have. Ft is equal to, the tractive effort is equal to 277 Fa. This is the component of force required to create the acceleration. Fa is equal to 277.8 W. Of course we have derived all these things in the previous slides. Plus Fr is W into R, resistance required, tractive effort required to overcome the resistance of the train, and plus or minus 98.1 Wg. This is the force required to overcome the gravitational pull, and positive for upward gradient and negative for downward. Now let us see, that's about the tractive effort which is to be considered for traction applications. Now when you consider the mechanics of power transfer, means how the power is generated and how the power is mechanical power is being transmitted from the traction motors to the driving wheels. So if you consider, there are certain parts that we have to consider in order to have this mechanical transmission of power from the generating part to the transmission part. The first one is traction motor, where the mechanical power is developed, and from there it will be transferred to the pinion of the motor, and therefrom it will be transferred to gear wheel, and finally from gear wheel to the driving wheel. So this is actually the hierarchy of power, mechanical power transformer from traction motors to the driving wheel. So here let me consider this diagram. Here D is the diameter of the driving wheel, and D1 is the pinion. So this is actually the traction motor. This is the motor pinion arrangement, which is connected to the same shaft of the traction motor, and this is actually the gear wheel, and this bigger one is the driving wheel. So here D1 is the pinion. The power transfer will be from pinion to the gear wheel, having a diameter of D2. So here D2 is the diameter of the gear wheel. Now here, whatever force is developed here, this force is being transferred from D1 to D2, and there from DT to this driving wheel capital D. I mean the diameters I am telling. Finally the output is going to be Ft, that is the tractive effort. And we know that the torque is going to be equal to force multiplied by the radial distance. So from that equation, if you consider, these are certain parameters that we are going to consider. Capital D is the diameter of the driving wheel, D1 is the diameter of the pinion, and D2 is the diameter of the gear wheel, and R is the gear ratio, which is considered as D2 by D1. So let us consider T as the torque exerted by the traction motor, and F is the tractive effort at the pinion, that is the input actually we consider, and Ft is the output, tractive effort is the output. Let us consider efficiency of power transmission from traction motor to driving wheel as eta, and Ft is the tractive effort. Now the gear ratio is going to be equal to D2 by D1 gamma. So torque is going to be given as the force multiplied by the radial distance. So a T is that this is actually the torque exerted by the driving motors, which is the force developed multiplied by the radius of the pinion is given as D1 by 2. So from this equation we get F as equal to 2T by D1 newtons, and this input force, when it is transmitted to the driving wheels, the output we are going to get as Ft as equal to the efficiency of transmission multiplied by F into, and it is the ratio of the driving, I mean the diameters of the wheels between which the power is going to be transmitted. That is the D2 is actually the diameter of the gear wheel, and the capital D is the diameter of the driving wheel. So between these two the power is being transmitted, hence we have to consider this ratio also in addition to the force. So finally we are going to have the tractive effort is efficiency multiplied by the input force multiplied by the actual D2 by D, between which the power is going to be transmitted. But here F is given as T into 2 by capital T, that is torque multiplied by 2 by D1. So now again this is going to become D2 by D1, we have considered it as gamma. So now the formula becomes now for the tractive effort as efficiency multiplied by capital T into gamma by capital D, 2 into gamma by capital D. So just I am rewriting it as so finally we are going to have the equation for another equation for tractive effort in terms of torque developed by the traction motors and the gear ratio and the efficiency of transmission, the driving wheel, diameter of the driving wheel as Ft is equal to eta multiplied by capital T into 2 into gamma, that is the gear ratio, divided by the diameter of the driving wheel. This is another formula for the tractive effort. So these are the two things that we have to consider. The first one is tractive effort expressed in terms of three components of force. One is Fa and Fr and plus or minus Fg. and another one is in terms of torque and gear ratio and diameter of the driving wheel. So depending upon the data we are given, we need to apply the formula. Okay, that's all for today's session. I request all the viewers to subscribe to my channel and give your valuable feedback so that I can make the videos in a better way for you. And this is Shiva Biram signing off. Thank you very much.